Welcome to this video on changes of state. We will explore how matter transforms between solids, liquids, and gases, and the energy changes driving these transitions. In this video, we will cover the 3 states of matter, the 6 types of changes of state, the relationship between energy and temperature, and finally, some essential exam techniques. Matter exists in one of 3 states: solid, liquid, or gas. A substance's state depends on its particle arrangement and energy. Understanding these arrangements is key to explaining changes of state. Particles in a solid are in a fixed, regular arrangement. In liquids, particles are close but disordered, allowing them to flow. In gases, particles are far apart and move rapidly. Solids have a fixed shape and volume because particles are held in a strong lattice. They can only vibrate in place and are effectively incompressible. Liquids have a fixed volume but no fixed shape, taking the form of their container. Their particles have weaker forces than solids, allowing them to flow and slide past each other. Gases have no fixed shape or volume and are highly compressible. Their particles are far apart with almost no forces of attraction, moving rapidly in random directions. This table summarizes the key properties of the 3 states, comparing their shape, volume, particle spacing, movement, and the forces acting between their particles. When a substance gains or loses energy, it undergoes a change of state. There are 6 main transitions between these states that you need to know for your physics exam. Melting occurs when a solid is heated and gains energy to overcome its fixed arrangement. Crucially, the temperature remains constant during melting, as energy breaks bonds instead of raising temperature. Freezing is the reverse process. As a liquid loses energy, its particles slow down and form a fixed solid structure at the substance's melting or freezing point. Boiling occurs when a liquid reaches its boiling point, allowing particles to overcome all attraction forces. Note that boiling happens throughout the liquid, whereas evaporation occurs only at the surface. Condensation is the reverse of boiling. When a gas is cooled, it loses kinetic energy, and particles are pulled together into a liquid, such as droplets on a cold surface. Sublimation is when a solid turns directly into a gas without becoming a liquid. Examples include dry ice or iodine crystals, which bypass the liquid phase when heated. To summarize, melting and boiling involve heating, while freezing and condensation involve cooling. Sublimation is the direct conversion of a solid to gas, and evaporation is surface-level liquid to gas transition. It is important to understand that changes of state are physical changes, not chemical ones. This means no new substance is formed, and the process is reversible. This table contrasts physical and chemical changes. Physical changes, like melting or boiling, involve no new substances and remain reversible, while chemical changes like burning or rusting create new substances. To understand changes of state, consider particle motion. Every particle has kinetic energy due to its motion. Higher temperatures mean higher kinetic energy and faster particle movement. Internal energy is the total kinetic and potential energy of all particles in a substance. When you heat a substance, you increase this internal energy. Heating a substance leads to a rise in internal energy. Depending on the substance's current state, this added energy either increases the temperature or drives a change of state. Cooling a substance removes energy. As particles slow down and lose kinetic energy, the substance may transition to a lower energy state, such as a liquid freezing into a solid. During heating, temperatures rise until a state change begins. At points like melting at 0 degrees or boiling at 100 degrees Celsius, the temperature remains constant as the substance changes state. A key concept to remember is that temperature remains constant during a change of state. Even as you continue to supply heat, the substance's temperature will not rise. Temperature stays constant because the supplied energy is used to overcome forces of attraction between particles, rather than increasing their kinetic energy or speed. When heating a substance, energy either increases kinetic energy, causing temperature to rise, or increases potential energy, allowing a change of state while temperature stays steady. A heating curve graphs temperature against energy supplied. Sloping lines show rising temperature, while flat horizontal lines clearly indicate where a change of state is taking place. Latent heat is the energy required for state changes without temperature shifts. It includes the heat of fusion for melting and the heat of vaporization for boiling. The formula for specific latent heat is Q equals M times L, where Q is energy, M is mass, and L is latent heat. This helps calculate the significant energy required for transitions. During melting, potential energy increases as bonds weaken. During freezing, kinetic energy is lost as particles lock into a lattice. Boiling and condensation involve full overcoming or forming of these bonds. Finally, remember the differences between evaporation and boiling. Evaporation occurs only at the surface at any temperature, while boiling occurs throughout the liquid at a fixed temperature. Let's look at real-world applications. Sweating cools the body because evaporating sweat absorbs latent heat from your skin. Refrigerators use a refrigerant that evaporates to absorb heat inside and condenses to release it outside. Dry ice sublimes at low temperatures, creating dense fog for theatrical effects. For your physics exams, precision is vital. Examiners look for a clear understanding of the particle model. The following tips will help you avoid common mistakes and maximize your marks when discussing changes of state. The most important tip is that energy changes state, not temperature. During melting or boiling, supplied energy is used to overcome forces of attraction between particles. Temperature only rises before or after a change of state. Mention intermolecular forces to fully explain why temperature remains constant. Avoid these common mistakes. Temperature stays constant during state changes, so don't say it rises. Changes of state are physical, not chemical, so no new substance is formed. Remember, particles remain the same, only their arrangement and energy change. Also distinguish between surface evaporation and bulk boiling. Master these key terms. Internal energy is the total kinetic and potential energy of particles. Melting and boiling points are specific temperatures for state transitions. Latent heat is the energy involved in these transitions at constant temperature. Sublimation is the direct transition from solid to gas. For a 4-mark explanation question, follow this structure. State that energy is being supplied, explain it overcomes forces between particles, clarify that potential energy increases while kinetic energy does not, and finally, note that since temperature measures kinetic energy, it remains constant. Test your knowledge with these quick questions. What is the solid to gas transition called? Why is temperature constant during melting? Can you name 2 differences between evaporation and boiling? And finally, how would you calculate the energy needed to boil water, given its mass and latent heat? Here are the answers. The solid to gas change is sublimation. Temperature stays constant because energy overcomes intermolecular forces. Evaporation happens at the surface at any temperature, while boiling occurs throughout at a fixed point. Use the formula Q equals mass times latent heat to solve the calculation. To summarize, know the 3 states of matter, the 6 phase transitions, and that these are reversible physical changes. Remember that temperature remains constant during phase shifts. Internal energy accounts for kinetic and potential energy, and use the latent heat formula to calculate energy requirements. You are now ready to tackle questions on changes of state. Remember to revise these definitions, practice past exam papers, and use precise particle-level language to ensure you succeed. Good luck with your studies.